Hi everyone, welcome back to Data Science in your pocket. And today we are comparing two very important things, that is TPU versus a GPU. Two architectures, two philosophies of AI compute. So, if you don't know why we're talking about TPU, I think recently Google has released Gemini 3 Pro, which is one of the best models in the town. And surprisingly, it is not trained on GPUs, it is trained on Google's TPUs only. So, in this video, I'll be explaining you the difference between the two and which one, as an AI enthusiast, you should use. Talking about the core philosophies, I think TPU is very application based. It is built only for neural networks. It eliminates wasted motion, maximizes data reuse, and direct data flow. While talking about GPU is more general purpose. It is used for neural networks training also, but it can be used for gaming, for video rendering, etc. It preserves programmability, handles diverse workload, and flexible scheduling systems. How TPUs think about compute? It is based on a systolic array, a grid of multiply accumulates units optimized for neural networks. We're not jumping deep into this, else this would confuse you all. We just going at a read to understand what does a systolic array mean. Fixed weight stream through the array, direct data flow between neighboring cells, maximize data reuse with minimal memory access, and unified buffers for high bandwidth data staging. So the way it looks at compute is quite different compared to a GPU. How does a GPU look at it? It is built on SIMT computing, a versatile architecture adapted for AI workloads especially. Thousands of threads across streaming micro multiprocessors, multi-layer memory hierarchy for flexible data access, Tensor Core accelerate matrix multiplication, and versatile precision for support. This is very important. GPUs can support different types of precision, FP64 to FP4, that is floating point, while in case of TPUs that is not possible. Precision, flexibility versus focus. TPUs are more focused. They prioritizes BF16 compute, floating point 32 accumulation, limited precision range. So they are not able to support everything. While in case of GPU, it can support wide variety of precision, floating point 64, BF16, FP16, FP4, FP6, FP8, and what not. The variety is higher. Power, performance, and the real cost of training. When you look at a modern TPU, it consumes about 300 watt efficient design optimized for neural network. While if you look at a top tier GPU, it consumes 1000 watt. Higher peak performance, general purpose architecture. What is the real cost? I think energy consumption is more than peak flops at scale. Modest efficiency difference compound. TPUs more work per joule. I think this is more important. While GPUs are unmatched single chip throughput is there. If you look at here, power consumption per million tokens served, Google TPU, it's quite less as compared to NVIDIA H100, but NVIDIA H100 is of the highest grade GPU. Do you remember that? So here you can see that H100 is consuming a lot of more energy. Memory, similar numbers, different behaviors. On paper, both platforms look similar with 192 GB HBM, but memory behavior diverges a bit. So the memory is a little different. TPU memory flow is unified buffers on chip, near shared across pod, highly structured flow, and reduced synchronization. While in case of GPU, complex caching hierarchies there, thread schedulers are there, excels at irregular workload. More data movement is there. Scaling beyond a single rack. Scaling exposes the strong architectural differences between TPUs and GPUs. So, talking about how does a TPU scale, I think 3D torus interconnect, optical circuit switch fabric, dynamic all-to-all connection, building scale machine. While GPU scaling is NV link inside racks, InfiniBand across racks, and tightly bound 7 to GPU domain packet routed networks. TPU scaling is exceptionally well suited for mixture of experts architecture. Do remember this. The Gemini 3 case study, I think for Gemini 3, the team has used TPU, and that is why TPUs have come into the news once again. It is a mixture of experts transformer, and hence it has been used for TPUs, sparse architecture with expert networks, require extreme cross chip communication, tokens continuously routed between experts, and demands complex synchronization. While TPU scaling fits perfectly for Gemini 3 because optical fiber enables free movement, Unified pod memory simplifies token dispatch. Lower cost, higher energy efficiency is there. The ecosystem trade-off, as you can see, talking about the GPU ecosystem, CUDA is a mature tool, PyTorch is there, kernel customization, cloud to on-prem portability is also available. While talking about TPU, I think JAX is a functional programming which is not that popular. TensorFlow is a matured framework that can be used. XLA compiler and slower debugging is there when you're working with TPUs. The trade-off: GPUs faster research iteration, less constrained, while TPUs are better for stable models with tuned pipelines. No single winner, to be honest. Yes, I think universal engines for AI research, GPUs can use a mixed workload, exploratory research, and developer friendly. TPUs maximum efficiency. If when it is required, TPU should be your go-to solution. Electricity to neural networks and co-design infrastructure highly focused. What should you use? I think for most AI builders, GPU should be your go-to solution, not TPUs. I think faster experimentation is there, more matured ecosystem, be it CUDA, PyTorch, Hugging Face. Easier debugging is there, community resources are ample. When to use a TPU, large stable models are to be used. Single run cost dominates. Access to TPU pods when you have access to it. Most of us don't have an access. And extreme distributed scaling. Until you are not operating at industrial scale, you might not require TPUs. So with this, it's a wrap. I hope this was useful for you and you understand what is the difference between TPU and GPU. Thank you so much.